A strange light appeared in late 2021 when astronomers noticed a faint glow far beyond Neptune, more than 20 astronomical units from the Sun. The glow pulsed with a steady rhythm, and each pulse suggested that something hidden in the deep cold was waking much earlier than expected. Specialists checked their instruments, but the signal did not fade and the pattern did not break, which proved it was not an error or a distant star. The source was a massive body moving in from the edge of the solar system, and its name was Bernardinelli Bernstein. What kind of visitor glows before it even feels the sun? Comet Bernardinelli Bernstein, also known as C2014 UN271, entered scientific records as the largest comet nucleus ever measured, and its sheer scale surprised every research team that examined it. The nucleus stretches almost 85 miles across, which equals 137 kilometers, and this size makes it more massive than 10,000 typical comets combined. Astronomers first found it inside old images from the Dark Energy Survey, and the discovery became more certain when Hubble and ALMA confirmed the same structure with sharper observations. These instruments showed a giant body moving along a strange path that rises almost straight up from the planetary plane, and this rare 95.5-degree inclination makes Bernardinelli Bernstein unlike any comet usually seen in the solar system. The orbit reaches out toward the far Oort cloud before curving back toward the inner regions, and the extreme shape of this route raised early questions about what changed its distant journey. Scientists believed the object should remain silent and frozen until it reached a point much closer to the Sun, but it started to brighten long before that moment arrived. Why would a frozen world wake before the heat that should set it free? The first sign that something unusual was happening came from a region of space where nothing should be alive. This region lies more than 20 astronomical units from the Sun, and at that distance the temperature is so low that even the hardest ice remains locked in a frozen state. Scientists expected every object in that area to sleep in total darkness because the sunlight that reaches it is too weak to cause any activity. Comet Bernardinelli Bernstein challenged that rule the moment it began to glow far earlier than predicted. Astronomers watched the early data with confusion because no comet had ever shown such behavior in such an extreme environment. The key moment arrived when ALMA began to record streams of gas rising from the surface of Bernardinelli Bernstein. These streams were not made of water vapor, which is normally the first material to escape when a comet warms. Instead, the jets were made of carbon monoxide, which is a gas that can escape at extremely low temperatures. The presence of carbon monoxide suggested that the interior of the comet held large pockets of frozen gases that had been trapped for millions of years. This finding surprised researchers because these pockets were releasing material at a steady rate that did not match the usual patterns seen in comet behavior. Measurements showed that the amount of carbon monoxide leaving Bernardinelli Bernstein was far greater than the levels predicted for an object at such distance. The jets were more than 30 times stronger than the models generated for distant bodies. This discovery forced scientists to question the structure of the comet because such intense activity suggested that the surface was not smooth or uniform. Instead, it hinted that the comet had a complex interior with channels and reservoirs that allowed gas to escape through specific points. This structure was unique among known comets, and it made Bernardinelli Bernstein appear more like a small world with a layered interior than a simple block of ice. The intensity of the activity increased over several weeks as new readings continued to confirm the stability of the jets. Astronomers monitored the different wavelengths of light coming from the comet and noticed that the brightness rose and fell in repeating intervals. These intervals were steady enough to create the impression of a pattern caused by rotation or internal heat. The brightness cycles were not random, and this fact raised questions about the deeper forces inside the nucleus. Each new observation added more evidence that Bernardinelli Bernstein was not reacting only to sunlight but to some internal process that remained unknown. The presence of carbon monoxide at such a high rate also added another layer of mystery because the gas usually escapes during the early formation of a comet. For this gas to remain trapped inside Bernardinelli, Bernstein suggested that the object had been protected by extreme cold for an incredibly long time. This preservation allowed the gas to stay hidden until some change triggered its escape. Scientists debated whether this change came from a slight increase in temperature, a structural shift inside the nucleus, or another unknown factor. No matter the cause, the release of carbon monoxide signaled that the comet was storing more ancient material than expected. The unusual activity made Bernardinelli Bernstein valuable for understanding the early solar system because the contents of its interior acted like a time capsule. By studying the jets, scientists could learn about the conditions that existed when the comet formed in the distant Oort cloud. This chance to observe such a well-preserved object excited the scientific community, and new studies were launched to analyze the composition of its gas and dust. The deeper question came from the realization that something had awakened the comet far earlier than expected. What force could heat a 100 trillion-ton body in the coldest part of the solar system? The earliest images captured by the Hubble Space Telescope offered a new clue about the true form of Bernardinelli Bernstein. Astronomers expected a rough and broken surface because most large comets are loose collections of fragments. Instead, the photographs revealed a compact structure that looked almost perfectly round when compared with the irregular shapes seen in typical nuclei. This roundness surprised researchers because it suggested a level of internal pressure that kept the surface balanced. Such a balanced shape hinted that Bernardinelli Bernstein was not a fragile object drifting through space, but a massive body with enough weight to mold itself into a sphere. The spherical appearance also challenged older ideas about how distant comets form, since most objects in the outer regions develop uneven shapes. If Bernardinelli Bernstein had maintained a round form for millions of years, then its internal structure must have stayed stable despite the harsh conditions of the Oort cloud. This stability led scientists to search for signs of deeper layers inside the nucleus that could explain the unusual shape. Temperature data from a range of telescopes began to confirm that the interior did not behave like a simple block of frozen materials. Instead, the readings showed several layers that trapped heat in specific regions while keeping other areas extremely cold. These temperature differences suggested that the nucleus held multiple shells made from different types of frozen gases that were arranged in a structured pattern. The presence of distinct layers meant that Bernardinelli Bernstein had somehow built its interior through processes more complex than the standard model of comet formation. Carbon monoxide played a major role in this investigation because the gas behaved differently inside each layer. The deeper layers held the highest concentrations of carbon monoxide, and these pockets responded quickly to small changes in temperature. This behavior created pressure inside the nucleus that moved toward the surface through hidden channels. Such movement made the comet appear alive in a mechanical sense because the interior reacted like a system rather than a random collection of frozen materials. As the comet moved closer to the Sun, Even the small increase in distant sunlight affected these layers and triggered new patterns in heat distribution. This energy shift created a repeating thermal pulse that appeared every 4 hours when scientists monitored the emissions. The steady rhythm of these pulses confused researchers because most comets show irregular heating due to uneven surfaces. The 4-hour cycle was too consistent to be random, and this consistency suggested that the nucleus either rotated at a stable pace or held an internal engine of trapped energy. If rotation caused the pulses, then the layers inside Bernardinelli Bernstein were arranged evenly around a central axis. If trapped energy caused the pulses, then the nucleus stored ancient heat collected during its earliest formation. Both possibilities pointed toward a complex origin that did not match the typical formation path of icy bodies in the outer solar system. The pulses also offered a way to measure the strength of the internal processes because each cycle showed slight variations in brightness linked to deep activity. These variations revealed how the layers expanded and contracted as carbon monoxide moved through the nucleus. The movement produced patterns that looked similar to breathing motions, giving the impression that the comet followed a natural rhythm. Such behavior fascinated the scientific community because no other known comet displayed a repeated cycle of internal heat. This cycle meant that Bernardinelli Bernstein could not be explained only by sunlight or distance, since the pulses continued even when the energy from the sun did not change. The evidence raised new questions about the early conditions that shaped the comet because the structure appeared too organized to be accidental. If Bernardinelli Bernstein preserved its layers for millions of years, then those layers contained information about the environment that existed when the solar system was young. The spherical shape, the layered shells, and the repeated heat pulses all pointed to a deeper story hidden inside the nucleus. Scientists watched closely as new data arrived because each observation strengthened the idea that Bernardinelli Bernstein might represent a rare class of structured objects. Was it simply a frozen relic from the outer darkness, or was it a world shaped by ancient forces that left their marks in every layer? The orbit of Bernardinelli Bernstein became one of the most startling discoveries because its path ignored nearly every rule that governs motion in the solar system. Most planets and comets move near the same flat plane called the ecliptic, and this shared layout makes their orbits predictable over long periods. Bernardinelli Bernstein did not follow this shared structure because its orbit tilted almost 95.5 degrees above the ecliptic. The direction of this orbit made the comet appear as if it were cutting through the solar system like an object entering the scene from another dimension. This sharp angle forced astronomers to rethink how such a massive body could travel along a route so different from the common patterns. Many distant comets have tilted orbits, but none of them reach the extreme angle seen in Bernardinelli Bernstein, given its enormous size. The scale of the comet made the orbit even more confusing because heavier bodies usually settle into more stable paths as they interact with gravity over millions of years. The path suggested that some major event in the past forced the comet onto this strange trajectory. Computer models helped scientists trace the route of Bernardinelli Bernstein back through time, and the simulations placed its origin deep inside the farthest regions of the Oort cloud. The Oort cloud stretches almost halfway to the nearest stars, and objects inside it move slowly in the dark for most of their existence. Bernardinelli Bernstein likely spent millions of years drifting quietly in that distant region before something changed its direction. The simulations showed that it followed a long arc that rose high above the solar system, looped outward, and then began a slow descent toward the sun. This descent could not be explained by ordinary gravitational drift because the orbit showed signs of a sudden shift. The sudden shift indicated that the comet experienced a powerful gravitational pull from something heavy enough to alter its million-year path. Scientists explored several possibilities, including the influence of nearby stars that may have passed close enough to disturb the outer edges of the solar system. Stars frequently move through the galaxy in wide arcs, and some of them pass near the solar system without being noticed. Even a distant star with moderate mass could push an object like Bernardinelli Bernstein out of its resting place with a single gravitational sweep. Research teams compared star maps with the modeled path to search for candidates, but no confirmed star matched perfectly with the estimated timing of the shift. This gap in the evidence opened the door to another possibility that had long been debated within the scientific community. Some astronomers believe that an unseen massive planet orbiting far beyond Neptune may be responsible for unexpected changes in the outer solar system. This hypothetical world is often described as several times larger than Earth and dark enough to hide from current telescopes. If such a planet exists, its gravity would be strong enough to drag a giant comet like Bernardinelli Bernstein into a new path. The idea gained attention because the orbit of Bernardinelli Bernstein shows signs of a controlled curve rather than a chaotic scatter. A controlled curve suggested that the comet may have been guided by a single source rather than random interactions. This guidance raised new questions about how often such shifts happen in the distant regions where sunlight is too faint to influence objects directly. The unusual tilt also suggested that Bernardinelli Bernstein approached the planetary region from above, where fewer physical obstacles exist. That approach made the comet act like a cosmic visitor that arrived from a vertical route instead of from within the solar system's original formation disk. The strange path gave astronomers a rare chance to study how gravitational interactions shape giant bodies over immense distances. The orbit also hinted at the possibility that other large objects may be hiding beyond the known boundaries, waiting for their own gravitational kick to send them inward. Scientists considered this possibility carefully because Bernardinelli Bernstein's size meant that any unseen companion capable of shifting it must also be significant. Each model that attempted to recreate the comet's past movement pointed to an external force that acted with precision. This precision fueled speculation about how the early solar system evolved and how many ancient interactions shaped the current layout. As the comet continued its journey inward, the unusual orbit reminded astronomers that the solar system is still influenced by forces far beyond everyday observation. If Bernardinelli Bernstein was redirected by something massive, then that hidden influence may still be out there in the dark. Who or what could have nudged this giant onto a course that breaks every rule? Light coming from Bernardinelli Bernstein became one of the most important clues because it revealed a pattern that no ordinary comet had ever shown. Most comets brighten when sunlight heats their surfaces and melts the water ice trapped inside them, but Bernardinelli Bernstein did not follow this rule. The brightness of the giant comet was shaped almost entirely by carbon monoxide escaping from deep layers, and this unusual behavior made the light signature stand out. Carbon monoxide responds to very small temperature changes, which meant that even a weak rise in radiation could push gas outward in powerful bursts. As the gas escaped, the brightness increased in smooth cycles that did not match the chaotic flicker normally seen in icy bodies. The first set of observations revealed that the brightness followed a repeating wave that rose and fell with surprising consistency. Each wave lasted just long enough to form a complete cycle that looked like a heartbeat moving through the darkness. The steady rhythm fascinated astronomers because comets usually respond to sunlight in uneven ways that create sudden flashes. Bernardinelli Bernstein did not flash unpredictably, but instead moved through slow pulses that kept their shape from one day to the next. The stability of these pulses indicated that the source of the brightness was not only the surface, but something deeper inside the nucleus. Scientists monitored the pulse pattern over several months and discovered that the rhythm stayed stable even as the comet drifted toward warmer regions. This stability showed that the process was not caused by random cracks or surface fractures, which often appear and disappear quickly. Instead, the pulses hinted at an organized system inside the nucleus that controlled how gas escaped through different channels. Such an organized system raised questions about the physical layout of the comet because it suggested that the materials were arranged in layers that responded differently to heat. If each layer absorbed and released energy at a specific pace, then the combined effect would create waves of brightness similar to the ones recorded. This explanation matched the earlier findings of layered shells inside Bernardinelli Bernstein, which trapped carbon monoxide at various depths. The way the light changed over time gave researchers a chance to map how the layers interacted with temperature changes. These interactions showed that the deeper layers reacted first and then passed the energy outward toward the surface in gradual steps. Each step created a pulse, and the pulse became visible when carbon monoxide pushed outward and scattered sunlight. The repeating sequence made the comet look almost like a living object that breathed in a slow and controlled manner. No known comet had ever produced such a predictable rhythm, which made Bernardinelli Bernstein stand out as a rare and valuable subject of study. The rhythm also allowed scientists to estimate how much gas was stored inside the nucleus because each pulse carried a different amount of carbon monoxide. These estimates suggested that the comet held an enormous reservoir of ancient gases that had survived since the earliest days of the solar system. The deeper question came from the timing of the pulses because they appeared to follow an internal schedule independent of external conditions. If the pulses were controlled by rotation alone, then the nucleus must have a perfectly balanced structure that turned at a steady pace. If the pulses came from other processes inside the comet, then those processes must operate like a natural timer that regulates each release of gas. Both possibilities pointed to a hidden system that kept the comet active long before sunlight reached it with enough strength to melt water ice. This hidden system made Bernardinelli Bernstein behave more like a structured world than a simple collection of frozen materials. The behavior raised new questions about how many other large comets might hold similar features that have never been detected. Some researchers wondered whether Bernardinelli Bernstein represented the earliest stage of a world that never fully formed. Others believed that the comet preserved ancient patterns of energy that were present in the solar system billions of years ago. Either theory suggested that the brightness patterns carried a message from a time when the planets had not yet taken shape. If the light pulses truly reflect an internal timer, then the comet may hold clues about forces that operated far beyond human understanding. Why would a frozen titan shine with the rhythm of something that knows exactly when to breathe? The mystery around Bernardinelli Bernstein grew deeper when scientists began comparing it with other strange visitors that had entered the solar system in recent years. The first comparison involved Oumuamua, which passed through the inner planets in 2017 without producing a visible tail. Oumuamua confused the scientific community because its motion did not match the behavior of known comets, and its shape suggested a structure unlike anything previously recorded. The absence of a tail forced researchers to consider new explanations about how some interstellar bodies release material in unusual ways. Bernardinelli Bernstein did not resemble Oumuamua directly, yet both objects displayed forms of activity that ignored the rules that usually guide comet behavior. The second comparison focused on Borisov, which arrived in 2019 and became the first confirmed interstellar comet with a composition far cleaner than expected. Borisov carried ice with almost no contamination, which suggested that it formed in a distant region untouched by heavy elements. The purity of those ices made researchers rethink how material groups together in the colder parts of the galaxy. Bernardinelli Bernstein showed a different kind of purity through its strong carbon monoxide emissions, which pointed to an interior that had remained sealed for millions of years. The third comparison involved the object known as Atlas, which appeared in 2025 and carried chemical patterns that challenged established models. Atlas exhibited a mixture of gases that did not match the expected signatures of a natural comet from any known region. The strange chemistry made the object stand out, and it encouraged researchers to check whether other giant visitors showed similar anomalies. Bernardinelli Bernstein shared some of these unusual traits because its brightness relied on carbon monoxide rather than water ice. The comparisons raised a possibility that made some researchers uncomfortable because it suggested that these objects did not arrive randomly. Artificial intelligence simulations run in 2025 introduced another surprising layer because they showed synchronized disturbances at the edges of the Oort cloud. These disturbances did not match the pattern of normal gravitational drift, which usually spreads out slowly across millions of years. Instead, the simulation suggested that something had pushed several distant bodies at nearly the same time. Researchers proposed two potential causes that could explain the synchronized movement across the frozen boundary of the solar system. The first cause involved the influence of galactic tides, which rise and fall as the solar system moves through the Milky Way. Galactic tides can shift the positions of objects in the Oort cloud by applying broad gravitational pressure. If the tides strengthened during a particular part of the galactic orbit, they could move multiple bodies inward during the same period. The second cause involved clumps of dark matter, which might pass silently through the outer regions and disturb the orbits of large icy bodies. Dark matter does not interact with light, but its gravitational effects are powerful enough to redirect objects along new paths. If a dense clump moved through the Oort cloud, it could have given Bernardinelli Bernstein the push that sent it toward the Sun. Some researchers believe this scenario explained the timing of the disturbances observed in the simulations. Other scientists refuse to rule out the possibility that several forces combined to produce the unusual patterns seen in the recent visitors. Among the more speculative ideas was the concept of an inbound wave made of unusual objects crossing the galaxy along with the solar system. If several objects formed in the same distant region, they might travel through space as a loose group rather than as isolated wanderers. This idea gained attention because it matched the arrival timeline of Oumuamua, Borisov, Atlas, and Bernardinelli Bernstein. The wave theory remained unproven, but it encouraged researchers to check for more evidence hidden within older sky surveys. Scientists who supported the theory suggested that the recent visitors represented only a fraction of the bodies currently moving inward. They believed that many objects remained undetected because their paths kept them far from bright regions where telescopes focused their attention. The idea that Bernardinelli Bernstein belonged to a larger pattern made its presence even more mysterious. If the simulations were correct, then the giant comet was not the beginning of a trend, but rather the first sample that appeared clearly enough to be noticed. This possibility raised a final question that echoed through the scientific community. What if Bernardinelli Bernstein is not the first to arrive, but only the first that humanity managed to see? Bernardinelli Bernstein stands as the largest comet ever recorded with a nucleus 137 kilometers wide. It remains active beyond 20 astronomical units, where sunlight is too weak to melt ordinary ice. Its carbon monoxide jets rise with 30 times the strength scientists predicted for such a distant body. Its tilted orbit of 95.5 degrees shows no clear origin and raises questions about its hidden past. The comet will reach its closest point in 2031 before disappearing for millions of years. Is Bernardinelli Bernstein a natural wanderer, a cosmic relic, or a message from a deeper age?